So in this video we'll see electric field intensity due to a short dipole. Short dipole means comparative to the distance of a reference point, the length of the dipole is very small, then that is short dipole. So due to that short dipole at any general point, not on axis of axis of dipole, not on equatorial point, somewhere we'll take it somewhere here at general point, somewhere here at n, what is the dipole moment, what is the electric field intensity, we'll see. Okay, at this n general point, say it is at a distance r, and what is the electric field intensity at point n, we'll see. Say it makes angle theta, the radius vector makes an angle theta with the axis of the dipole, and here minus q plus q. Every time we need not to write this, but just for understanding purpose we are writing. Always dipole moment acts along minus p2 plus minus q2 plus q. This is the direction of the dipole moment. See here, very interesting point. To solve this type of problem, same approach you can follow whenever a numerical or anything is problem is asked in the exercises or examinations. A simple thing. Here, let us resolve this p bar into two rectangular components. So here we are resolving the dipole moment into two rectangular components. This is one along the radius vector. Okay, one is along the radius vector. This is this one along the radius vector, and normal to that another one. So thus that radius the dipole makes theta angle with the radius vector. So this component will become p cos theta. So what we can assume is it is a dipole with the dipole moment p cos theta, and this component becomes p sin theta. See here, very interestingly, very important point you can see there. The point n is on axis of p cos theta dipole. Okay, this is p cos theta dipole. Let me write it as some AB just for understanding purpose. So AB is the p cos theta, one of the component of given dipole. So on that AB dipole, on the axis of AB dipole, the point is present. Okay, so then what is the electric field intensity when it is on the axis of the dipole? So the dipole, first dipole, total dipole moment you can write as p bar equal to p cos theta plus p sin theta. P1 bar plus P2 bar, or P1 is P cos theta plus P sin theta. Okay, we resolve into two components. So this P cos theta is one, you can take as one dipole, and P sin theta also can take as another dipole of dipole moment P sin theta. This one P cos theta. So therefore what we can write is this point n So point, what we can write here, what we can understand, point n is on axis of p cos theta dipole. Therefore, what is the electric field intensity or electric field strength on the axial line? Let me write it as E1. Okay, so here p bar equal to, we'll write as p1 bar plus p2 bar. So p1 is p cos theta, p2 is p sin theta. So what we can write, E1 on the axis of the dipole, what is the formula? K into 2p, the dipole moment. Actually, what is dipole moment here? P cos theta. 2p cos theta divided by distance is cube of the that distance, so r cube. Clear? Similarly, see here we have taken as AB as P1, and P2 is there. No, let us take as CD. This CD dipole is P2 dipole. What is the dipole moment? P sin theta. So this CD, see, I am writing a parallel this thing. This is CD. Where is N? It is on the equatorial point of that dipole. Therefore, E2, what we can write? What is the E2 equation? E2 is equal to K P by R cube, that is Kp sin theta. Here dipole moment for that is P sin theta. Kp sin theta by R cube. Therefore, the total net electric field due to short dipole we can write as root over E1 square plus E2 square. Simply square them and substitute. Finally, you will get P Kp by R cube root over 1 plus 3 cos square theta. 1 plus 3 cos square theta. So here K is how much? 1 by 4 pi epsilon naught. This is also very interesting one. And what is the direction of electric field? See here in the diagram at this point N, the electric field intensity due to AB dipole, that is P1 dipole, is in this direction. And what is the direction of on the equatorial line? It is opposite to the dipole moment. Direction of CD, the dipole moment direction of CD, that is P2, is in this direction. So opposite to that, parallel, anti-parallel to that. This is the direction of, see here, this is I am writing E1 and this one will be E2. The net electric field direction will be this E. So say this makes angle some alpha here. The net electric field makes angle alpha with radius vector. We are taking angle with radius vector. Again here we'll see the diagram. This is the dipole. We resolved this into two components. One is along the radius vector. This is the radius vector. Here point N is there. So due to that dipole, the direction of electric field will be in the direction of dipole moment. This is E1 bar. Okay, this dipole has along the radius vector, and this dipole that is CD. This dipole moment direction is P. Direction is from C to D. What is the electric field direction due to that? E2, in this direction. Therefore, the net electric field direction will be like this, E. Say it makes an angle alpha. This is alpha angle. When it makes an angle alpha, simply tan alpha is equal to how much? In the diagram, you see the diagram, what is the tan alpha? Yes, exactly, E2 by E1. E2 by E1 means, if you substitute those value of tan, see what is the angle we took? Theta. This is the angle theta we took. So of tan theta, so tan alpha equal to of tan theta. You can find out what is the direction, what is the direction of the net electric field using this. Okay, so this is the important concept. In the next video, we'll see another topic.